Welcome to Know-How. In this video we will look at the discharging of an RL circuit, and then we will solve the differential equation and look at the transient response. So what we mean by discharging here is, so we took an RL circuit. In a different video I had an RL circuit, RL in series, and we connected the RL circuit across a DC voltage source V using a switch S1, and we observed what the steady state current flowing through this circuit was. So we noticed that I of t, or I of 0 after steady state at this condition right now, I of t is V over R. So when it reaches steady state, the current goes to V over R, and this is IL of t, and the VL of t starts initially at voltage V across the inductor, and eventually the inductor became a short, and at time t equal to 0, for our reference right now, this is t equal to 0 for us, because now we are trying to discharge this circuit and see how it performs. So now we had another switch S2, and what we do now is we open the switch S1 and we close the switch S2 at time t equal to 0, and we wrote the initial conditions here. So the current is V over R that is flowing, and then the voltage is 0 across the inductor. So now let's write the KVL for this loop here. So the 0 is the voltage, because now we shorted it to ground. There's no voltage between these 2 points. So is I of t multiplied by R plus L di of t over dt. Now we isolate the term that has the derivative, so we get 0 is I of t. So basically we divide both sides by L, so we get this. And this type of differential equation can be solved by finding an integrating factor, and that integrating factor depends on the coefficient of the term that does not have the derivative. So IF in this case is e power t R over L. So now we multiply both sides with the integrating factor. So we get 0 is e power t R over L, and basically let me put the R over L before, that was already existing, I of t plus di of t over dt e power t R over L. So now if you look at this term here, this is nothing but the derivative of this term here. So we have a derivative of function multiplied by I of t, and then we have the derivative of I of t multiplied by the same function. So this would be d over dt, the function 1, which is e power t R over L, multiplied by the function 2, which is I of t, is 0. Now we integrate both the sides with respect to dt. So what we get is, say, you could put the constant anywhere. Say, let me put the constant on this side. Constant is e power t R over L multiplied by I of t. So now let's multiply both sides with e power minus t R over L to isolate I of t. So I of t becomes k times e power minus t R over L. Now we know what is the initial condition for the current. So initial condition, we know that the I of 0 is V over R. So I of 0 is V over R becomes k, because at t equal to 0, this is at t equal to 0, this e power minus t r over L becomes 1. So V over R is, the K is V over R. Or we got this I of t is V over R e power minus t R over L. So what happens here is the current, if you plot it across with time, with respect to time, so it started at V over R and then it dies down exponentially towards 0. So now let's look at the voltage across the inductor. VL of t, you know, it is L di of t over dt, which would be L V over R, or e power minus t R over L, and then multiplied by minus R over L. That would be equal to minus V e power minus t R over L. This is VL of t. So it's basically, here what I did is I took the I equation, I of t here, and differentiated that to get this value inside here, and we got this equation. And notice that the negative term here, so you see that the voltage, so voltage was 0 initially, and then it suddenly becomes negative at t equal to 0. If you see now, the voltage becomes minus V and then dies down back to 0. So if you plotted the voltage and the current, both of them, so we saw that the current was V over R and dies down to 0. This is I of t, and V over R, this is with respect to time. This is when the RC circuit is discharging. And if you looked at the voltage, voltage was initially with 0, it jumps up to minus V and then dies down back to 0. So voltage is minus V, it start off here, this is VL of t, and then it goes back to 0. So, and previously when we looked at the charging conditions, what happened was the I of t came up from 0, it went to V over R, and now it discharges. And whereas the V of t was, it shot up to V initially, there was a voltage drop plus V and it died down back to 0. And now it goes to minus V and it goes back to 0 again. So what happens is, in this case, the current has not reversed direction. Like unlike the RC circuit where the current flows back, now the current is still flowing in this direction. It dies down, but the voltage across the inductor has kind of reversed initially, and then it goes back to 0 again. So this is how the current and the voltage look.